In this problem, we're looking to find the potential difference that is needed to stop an electron that has an initial velocity that's given to us in the problem statement. Now first off, recall that potential or potential difference is related to potential energy. Specifically, a change in potential energy is equal to the charge on the particle multiplied by the potential difference, or delta V. And that delta V is what we're trying to find. In the case of this problem, however, we want to relate these variables to the particle's initial speed, which means we'll actually want to connect this to kinetic energy rather than potential energy. Now this is a place where it's important to understand the law of conservation of energy. Because if energy is conserved in this system, then the change in potential energy must be equal to the opposite of the change in kinetic energy. So Q delta V must also be equal to the negative of the change in kinetic energy, or delta KE. So to find what this problem is asking for, we want to take this equation and solve it algebraically for delta V, because that's our end goal. So let's take both sides of this equation and divide it by Q to find that the potential difference, delta V, is equal to the negative of the change in kinetic energy divided by the charge Q. Now, of course, when we have that delta symbol in front of a variable, that just means we're taking the final value and subtracting the initial variable. So this could be read as the negative of KE final minus KE initial. And that is being divided by Q. But since we have this negative sign on the outside of the parentheses, it would be even simpler to just take away the negative sign and then flip the positions of the initial and final kinetic energy values. So we can write this as kinetic energy initial minus kinetic energy final divided by Q. Now recall that our purpose in this scenario is that the electron has some initial velocity, but we want to stop it from moving. And once that electron stops moving and its velocity is zero, then it has no kinetic energy either. So the final kinetic energy is zero. So really, our equation can be most simply written as delta V equals kinetic energy initial divided by Q. And recall from our energy units that the kinetic energy of some particle is equal to 1/2 multiplied by the mass of that particle or object multiplied by the square of its speed. So we should substitute that in for our initial kinetic energy value. So delta V becomes equal to mv squared divided by 2q, where I've moved that 2 into the denominator. And really, all that is left for us to do in this problem is to substitute our values that were given in the problem into a calculator. So first off, for the particle, we're told in the problem that it is an electron, and so we should know, or you can look it up if you don't already have it memorized, that the mass of an electron is 9.11 times 10 to the power of negative 31 kilograms. This is being multiplied by the square of the electron's initial speed, which is given directly in the problem as 6.0 times 10 to the power of 5 meters per second. And don't forget to square that speed. And then we divide this by 2 multiplied by Q, which is the charge on the electron. And since this is a single electron we're dealing with, its charge is just that of the negative elementary charge. So that is negative 1.60 times 10 to the power of negative 19 coulombs. So, all that putting into a calculator, and we find a value for the potential difference of negative 1.025 volts. Or if we want to round this to adjust it to the proper number of significant figures, then we can instead write this as negative 1.0 volts. And that is our answer to the problem. I hope this video helped you out. If it did, please consider subscribing, as that'll help me out in making more videos just like this. If you have a request or a question, leave a comment down below. And I hope you all have a lovely day. Bye-bye.